Alrighty, welcome back. So, this is really where the action starts to some extent. Chapter one is sort of an introduction and a little bit of a history, which is cool. Chapter two, of course, was all about the scientific method, making sure you really understood why psychology is a science and preparing you for the science you're going to run into as we go through the rest of this course. Just to appreciate the process, I guess, that every psychologist or every experimental psychologist at least is going through in hopes of getting to the truth, getting to knowledge. So what we're going to do in the remaining chapters now is start looking at how people are doing just that. So we're going to jump into different topic areas, each of which sometimes represents a different approach to psychology. We can talk about this in a couple of ways. There are different, what we're going to call levels of analyses. We want to all understand ourselves, but there's various levels to kind of focus on. And a great example of that will be the chapter we're going to discuss now, where it's going to be very much the biological level, the level of the machine, so to speak. But of course, we can go up to the behavioral level, to the sociological level, all sorts of levels. And people do study human behavior at all these different levels. So every chapter might be a little different. It's like a different group of psychologists studying a different sub-part of psychology, sometimes using different methods or techniques. And so that's the challenge of this course, by the way. Not that anything is too tough, although this chapter can get a little tough at times. I'll be honest with you there. But more that you just have a lot to learn, because every chapter is like something new and different, and you're going to have like 8 of them by the time you're through here. However, the good news is they are almost all interesting and fascinating. At least, some you'll love some more than others, depending on your natural interests. But it's all pretty cool. So I think this is where, things get fun and we start literally telling you about yourself. So let's start here. Chapter 3, Lecture 1, The Machine That Is You. Dum-da-dum. And I want to kind of hearken you back to Cartesian Dualism. That I introduced you to. And remember, that was Descartes' notion that there was sort of two senses, two aspects of ourselves. Let's just read this. On the one hand, I have a clear and distinct idea of myself, insofar as I am a thinking, non-extended thing. On the other hand, I have a distinct idea of body, insofar as this is simply an extended, non-thinking thing, and accordingly, it is certain that I am really distinct from my body and exist without it. Okay, so René is arguing for a body and a mind that are distinct. And that's the dualist notion. That yes, he thought, the bodies that we have and that animals have are really complex machines, really fascinating. And in fact, as you'll see, Descartes' ideas started to kick off people thinking of bodies that way and studying them that way. But he also thought, but there's this other thing called mind, and it's where all the thinking happens, and it is distinct from the body. This is what Descartes believed. Now, following Descartes, a lot of other philosophers pushed things a little further and postulated what's sometimes called materialism. There's a number of materialisms. This isn't how much stuff you own. What this materialism is a reaction to dualism. So the concept of dualism is that our mind is more than just our brain, that it's somehow distinct, it's somehow different from the rest of our body, which is largely just a machine. But materialism states that there exists no spiritual entity, and everything is just physical matter. So to a materialist, we are totally machine. And any sense we might have of a spiritual component or a soul or a consciousness that feels non-physical is an illusion. They would say these things emerge from the working of the machine. They are part of the machine. And therefore, you can apply science to it and understand it. Okay? Most scientists, most psychologists are pretty far along the materialist. Like if we go kind of like how much do they believe in a soul versus, in the machine versus just a pure materialist thing. Obviously people are on different continuums, and some scientists do have a very spiritual side of them, but they almost all think that whatever they're studying, whatever their topic is, that it comes about from material processes that can be studied. That's why they're studying it. Otherwise it would be ridiculous to study it if they thought it was a spiritual basis. And so a lot of science has kind of given way to a more materialist perspective. And that really started with Descartes. In fact, Descartes already kind of opened that door with animals. Prior to Descartes, people thought that animals might have a soul as well. But when he did his dualism thing, he also distinguished us from animals and said, hey, we have a mind and a body. They just have a body. All you see with an animal is a body that's reacting to the environment, just instincts, just very, basic responses to stimulation. That's what it is. So a lot of people in Descartes' time started thinking, okay, let's study this machine then. That's fascinating. And it started a very controversial part of research that's controversial to this day. Not as controversial as I think it should be. But it's a notion of vivisection. Now, I'm showing you, this is still going to be kind of gross, what I'm going to show you on the left here. Once I walk you through it, you'll realize how gross it is. I asked... if you really want to see gross, Google vivisection in the images. So vivi, V-I-V-I, means living. Section means to cut, to section. And the notion after Descartes that became popular is if you want to understand this machine that is the body, you have to cut into it while it's alive. Because that's when it's working, right? Once it's dead, the machine stops, and you want to see the machine in action. And so because René Descartes said, hey, there's no soul in those animals, they were now fair game, okay? The religious orders said, okay, go ahead, you can do whatever you want to animals, there's no soul in the animals. And people began doing vivisections. And it was controversial at the time. A lot of people were saying, is this ethical? Is it right to be doing this to animals? And of course, the push for it was, well, we want to understand this body, and we have bodies too. So if we understand the bodies in animals, we'll be understanding our own, and there could be great benefits that come out of that. Okay, true. But how much will you give up your ethics for great benefits? Where is the line? And a lot of these people didn't think there was an ethical problem at all. And it's because of the way René described animals. I want to give you an example just to provoke your thought. This is how I think René would describe it today if he could, but he didn't have access to the 401 and cars going fast that I'll describe to you. But let's do that. So let's say you are on the 401 and you are sort of at the top of a hill, and on the one side of the hill you can see that the traffic has jammed right up to a standstill. On the other side of the hill you can see a car coming really fast. Okay, coming really, really fast. And you know that when that car gets to the top of the hill, it's going to see the standstill and it's going to have to stop really, really quick. And so you're watching this, and here's what you see. You see the car coming up really fast, and then suddenly you see the car scream. And all this shuddering starts to happen as the brakes kick in, right? So the brakes are on hard. We're seeing squealing. We're seeing all sorts of shuddering, and maybe the car even turns over. Maybe it crashes a few times and rolls because it was just so dramatic that it had to stop that quick. Okay, if I ask you now, after everything you just saw and heard, do you believe that car is alive? Well, you would say, no, it's not alive. And I'd say, well, what about the screaming and the shuddering and the violent actions? Isn't that the act of something in pain and something just about? And you'd say, well, no, it's a machine. It can't be in pain. It's just a car. I mean, maybe the driver's in pain, but the car itself, all of those things that kind of look like pain, they're not really pain. That's just what a car does when you put it under that kind of stress of going from very fast to trying to stop it up. When you cut into a living animal, it screams, it shudders, it does all sorts of things. And people would say to René, hey, are you sure this thing doesn't have a soul or whatever? And he'd say, no. that's just what this machine does when it's put under the stress that you're putting it under. You're doing things that could make the machine malfunction, cease to work. And when you do that, it reacts in these ways, but it doesn't really feel any pain. Just like the car doesn't feel pain. It doesn't feel any pain, and you're not going to be in any trouble. In fact, one of the things Rene Descartes said is, if it bothers you a lot, maybe the first thing you want to do is cut the vocal cords of the animal, and then it can't scream. Okay, for me, that just makes me go, oh my goodness, the depth of but never underestimate a human's ability to just put a wall emotionally between them and something, especially something they're studying. And so vivisection became very popular. People became fascinated by what they were learning about the respiratory system, about etc. This is the time when humans really started to say, wow, at least the bodies of things are this amazing, amazing machine. I told you about Luigi Galvani, right? With the electrical, showing that muscles reacted to electrical stimulation. This is that same sort of time, 1800s. The same time, by the way, when Mary Shelley wrote the famous book Frankenstein. And, none of this is coincidence. Mary Shelley was very connected to the science of the day. She knew about all this fascination with the body. And the idea from Luigi Galvani, and you'll see others here, that it was all about electricity somehow. So what's the story of Frankenstein? The story of Frankenstein is about a doctor named Frankenstein who creates a monster, who, by the way, wasn't originally named Frankenstein. This is Frankenstein. This isn't. Things got blurry with time. This guy was always described as the monster in the books. But the idea was they sewed him together from body parts they got from graveyards and stuff. So they got a bunch of leftover human body parts, sewed them all back together. This is like putting a car together from parts, right? We took this human body and we put it together from parts. And then, well, what did they do to bring it to life? Well, you kind of see it over here. Electricity. A shot of lightning is usually what's shown in these things. A shot of lightning that hits something and strikes this body and suddenly animates it. I'm alive, right? All of that is a direct reflection. Think of Frankenstein when you think of this time, because that story is a direct reflection of the science of the time. And it was a science that was increasingly interested in the body of animals, but also, I've told you a little bit of this with Broca's work and others, it started to extend into the bodies and brains of human beings as well. And so a real fascination with what we would now call biology, right? The biology of the human body and of biological bodies in general. Okay, so let's talk a little bit about that biology, but I'm going to be a little high level on this, and I'm going to do it for a reason, as I'll describe. But let me just, start with some of the typical stuff. When you start diving into the machinery that makes us, who we are, this body that is able to do its amazing things, you can do things like take parts of the body or parts of the brain, and you can stain it with certain stains and put it under a microscope and kind of see, well, what are the building blocks of this machine? And what you see when you do that, especially with brain tissue, are things like this: a set of interconnected, wiry looking things with globs here and there. And in fact, if you look at them closely, you see they kind of got wiry looking things on one end to a glob, and then they have a sort of tail, whatever you want to call it, that maybe connects to other wiry little blobs. So ultimately, this is the neuron. Okay, and so I've taken this sort of a slide view and made it a stylized view here. But this is the neuron, and we think this is the basic building block of who we are. This is where the smallest bit of information transmission happens. So if we want to understand the machine, we probably want to understand this lowest level of communication, this lowest level of sort of organized behavior occurring within us. And so we ultimately now know a lot about these neurons. These little wiry things at the end we call dendrites. This thing in the middle we call a nucleus. This is generally called the axon. this sort of tail that comes out, and it ends in what's called the axon terminals. So a little bit here. In general, this is called the cell body. Sorry, I should have said that. The cell body contains the neuron. And then around the axon, is this sort of globby little fatty stuff called the myelin sheath. Really important to keep the transmission efficient, and to also prevent short-circuiting, literally, to prevent neurons from stimulating each other in the axon part where you don't want that to happen. In between these myelin sheaths, we have these Schwann cells that make up the myelin sheath, and then in between we have these little nodes of Ranvier. All this to say, people like take close-up pictures of these things and see all this stuff, and everything's got a nice little name and nice little label. Of course, what we really want to know is, how does this thing work? What's it doing? If this is the basic sort of processing that's happening, what is the process that's happening? Okay, I created this slide. I hope it's not too much. Boom. We'll see. It's not too much, I don't think. Okay, let's start over here. So here's our buddy again, our buddy the axon. And now I'm going to try to tell you the story of this dude and his typical working day. Okay, so first of all, a neuron like this receives stimulation from other neurons via chemicals those neurons release that stimulate the dendrites of the receiving neuron. Okay, so right now this is the receiving neuron, and it's getting signals from other neurons in its dendrites. These signals, we'll talk more about this as we go through. In fact, we'll talk about synaptic clefts and neurotransmitters, all sorts of fun stuff. But for now, let me just say that the original neurons release some chemicals called neurotransmitters. Those chemicals are picked up by the dendrites of this axon. And when those neurotransmitters stimulate the dendrites, they do one of two things. They either make it more likely this neuron will fire. I'll explain what I mean by that in a moment. But they either make it more likely that it'll do that or less likely. If they make it more likely, we call those excitatory signals. It's sending excitatory signals. It's trying to convince this neuron to fire. But other neurons at the same time might be sending inhibitory signals. They might be trying to get this neuron to not fire. So it's kind of like this neuron is listening to a wide community of other neurons. And some of that community is saying, hey, there's something going on, you should fire. And others are saying, no, don't. Okay, so what's it do? Well, that's determined by the nucleus. All of these signals come in and they lead to a sort of chemical reaction that goes on. This is there's always a negative charge in here. It's always tricky to know how much details. There's always a negative charge here, but the excitatory signals make that charge a little more positive. And if they in fact make it positive enough, so literally what this is kind of doing is summing all the inputs, all of the neurons telling me to fire and all the ones telling me to not fire. I kind of add all that together. And if there's enough telling me to fire, if the amount telling me to fire is enough bigger than the amount telling me not to, and by enough, we mean there's a threshold, a certain amount of charge is what it literally is. That if the charge gets to a certain level, then I'm going to fire. Okay? So really the nucleus is making a very basic mathematical decision. It's adding together these excitatory and inhibitory signals and then comparing that to a threshold. And if it's strong enough, if it's excitatory enough, then it will fire. Okay. What does fire mean? Well, what that means is it's going to start a reaction, electrochemical reaction that's going to work its way down this axon and ultimately will encourage the release of chemicals from the axon terminal. So let's sneak over here now. So when a node is said to fire, this action potential, that's what we call it. It's really a change in the resting state of the axon as we go through. I'll show you in just a second. But let's just for now, here's the analogy I like. I like you to think of the following analogy. You know when you're at a sports game or if you see them on TV and you see people doing the wave, right? If you think of how the wave is done, the claim is you don't need to know. I mean, sure, you might watch the wave travel around the whole thing, but you don't need to know when to do your thing. Let's say the wave was moving this, now let's say it's moving this way across me. Okay, it's going to come from that side and it's going to move this way. All I really need to know is what the person beside me, or maybe one, maybe a couple over, all I need to know is what they're doing. And when they stand up and go down, then it's my turn to stand up and go down. So if I just, even with a one person beside me, if I just paid attention to the one person, and when they stood up, I stand up behind them, and when they go down, I go down behind them. If I just do that one simple thing and pay attention to that one very local bit of information, that can give rise to a wave that spreads right across the whole set of fans, right? So even though every individual fan is really just reacting to what's going on around them, we see an emerging wave that goes across the whole thing. So think of this as the wave, the action potential as the wave, but it happens because of a bunch of little decisions, as though a person were there just paying attention to what happens right around them. And then whatever happens causes them to change, which causes the next person to change, the next. And so what we end up with is this electrochemical signal. I'll show you more details in a second. Electrochemical signal that goes right down the axon. And then when it gets here, it produces or results in the release of neurotransmitters here. Remember those chemicals I was talking about over here? Well, this guy will release its own chemicals as well. So when a node is said to fire, an action potential travels down its axon, ultimately resulting in the release of neurotransmitters from these axon terminals. These neurotransmitters will now connect with the dendrites of another neuron over here, right? So just imagine this is a chain or a bunch of interconnected. And so this is now going to connect with another neuron and either excite or inhibit it. Okay, so this is the basic thing, a whole bunch of these interconnected neurons that are getting input from a subset of neurons. Based on that input, they are making decisions to fire or not, and then passing that decision on to stimulate other neurons. This intertangled group of very simple things are able to produce very complex behavior, kind of like the wave. Not that the wave is that complex. Okay, I'm going to leave it there for a second. I'm going to move to here. So the important thing, and we knew this, right, from Galvani's work, and I mentioned this with Frankenstein, but this is getting to the real guts of it here. We are ultimately electrochemical machines. By the way, Descartes, who's pretty smart in lots of different ways, he thought we were hydraulic machines. After seeing those hydraulic statues and knowing that we're full of liquid, he thought liquid was what pushed us around somehow. He was wrong about that. It's electrochemical. So it's literally, chemicals that are being released that have charges associated with them. So for example, sodium and potassium are two big players that have positive charges associated with them. Okay. So basically, remember what I told you that the cell body was negative? It rests at a negative, like around negative 70. You see it down here too, around negative 70. But when enough excitation comes in from the dendrites, then that starts to get less negative, right? It's going towards zero, less negative. And if it gets enough, hits this threshold, that will start the action potential. So what is this actual action potential? So what this has done is it's zoomed in on a little part of the axon. So we're imagining an action potential coming down here, and it's saying, okay, let's zoom in on here and let's blow it up here. And what we want to look at is the chemical gradients and the electrical gradients, because what happens as things happen are little gates open, sodium gates and such, that allow sodium and potassium to flow from the outside of the neuron to the inside of the neuron. That changes the electrical values, both outside and in, which ultimately changes the gradient, and it makes things want to flow in. But at certain points, there are sodium pumps that push the sodium back out. And so when the sodium comes in, that makes this area get really positive. But then when it gets pushed out again, it becomes negative. And so what we have is this positive charge that's flowing flowing down the axon, much like the waves, except instead of arms being raised, it's a positivity that comes up and then goes down. In fact, this is what you're actually seeing here, that as the sodium starts to come in to the neuron, to the axon, then we see it go really positive inside. But once we kick open the potassium gates, then the potassium flows out, and we see it, in fact, go down. And it doesn't even just go down to resting, it goes way down. So hyperpolarization, it goes much more negative inside for a while, and then it reestablishes its balance state, its resting level. So there literally is this, as chemicals flow in and outside the neuron, there's this spike of positivity that moves all the way down, and you can actually measure that. So something sensitive to electrical activity can measure this electrical current, and it is a current flowing down the axon. Okay. This stuff is, pretty complex at some level, and it's all about chemicals and electrical currents and all this kind of thing. I've given you a taste here. The textbook will also try to give you a taste. These are complex things, and I suggest to you that this is a time when you want to embrace self-directed learning. There are places where simulations work so much better than words. Someone like me trying to talk to you and using a figure and doing things, okay, we can do whatever, but let's show an alternative. What I'm going to recommend you do every now and then is, sorry, I should have just had this all blown up and ready to go here, is to do things like this: action potential in neurons. If you were listening to me, reading the textbook, and you're saying, I just don't get it, man, you're not being clear, I'm not with you yet, see if there's somebody else. And there are, if you go to YouTube and look at things. So let's look at a short one. Here's an neuron action potential made easy. Let's see.
I think we should explore a few solutions.
Grammarly suggestions catch.
In this video, I'm going to explain an action potential. An action potential, or a nerve impulse, causes a movement of ions across the cell membrane of a neuron, similar to a ripple passing along the surface of a pond. The cell membrane of a neuron contains thousands of tiny molecules known as channels. These channels allow either sodium or potassium ions to pass through. Generally, the channels on a neuron are closed, and the membrane is said to be in a resting state. In this state, the charge of the inside of the cell membrane is more negative than the outside. And if you could imagine sticking microelectrode connected to a voltmeter inside this membrane, the reading would show about negative 70 millivolt, meaning that the inside of the neuron is about 70 millivolt less than the outside. The cell membrane of a neuron is polarized because of this electrical difference across the membrane. Now, a nerve impulse starts when pressure or other sensory inputs disturbs a neuron's plasma membrane to the point that the potential difference reaches a threshold voltage of about negative 55 millivolt. This causes hundreds of sodium channels.
So right there, one of the things you're going to notice when you do this stuff is by watching 2 or 3 different things, you can fill in the missing parts. So, for example, he's already starting to talk about an action potential, but he hasn't really talked about what caused that action potential. The cell body receiving input from the dendrites that were summed, and so that part of the story is not being told here. But it will be told in some other video. And by listening to different people explain the same basic thing to you in 2 or 3 different ways, that's a really powerful way to ultimately get a much deeper understanding of what you're talking about. And because, online you can get richer animations like this, just the way he's, building things up and animating it in this powerful way, it can really help with the more complex stuff like this. So I'm not going to go into more detail. I'm going to leave it for you to kind of explore this world a little bit more. Read the textbook, see if it all makes sense to you. Watch, my lectures, see if that makes sense to you. If it still doesn't quite get there, do some self-directed learning. It can be really powerful. And I'm going to mention another aspect of that here. So when we get into this version of the course, I'm a big fan of this 3D brain. You can just look for 3D brain if you want. The exact, it's brainfacts.org/3D brain if you want. This is a really cool brain that you can grab, you can twist around, you can do things with. You can actually, one of these is a scalpel. Is this a scalpel? No, this is for annotating. Somewhere there's a scalpel. You can get in there and do stuff. But there's also, like, when we talk about different parts of the brain, we might talk about, we did talk about Wernicke's area. Let's see if we can find Broca's area here, which should be part of the frontal lobes. Let's see where there it is. So that was part of the frontal lobe area, different parts of it there. And if we go to Broca's area, there you go. You see where Broca's area is, and it gives you some information. You can grab it and, it will only it'll only give you a limited ability to turn when you got an area like this. That's cool. But it'll give you information about that. And as we go through the brain, it's really kind of cool to kind of go through these different areas and say, okay, tell me more about the nucleus accumbens. Where are they? Oh, there they are. And you can see right in the brain and get an idea of what they're doing, what they're up to. So this is a really good resource. And I really suggest when you've been reading for a while and you're like, oh, this is all hard on my head, it's fun to come in here and play with the brain a bit, do various things with it and learn this way as well. Okay, so both of those are my pitch for you here today, that especially with chapter 3, don't just stick with my lectures and the textbook, especially if you don't really understand something and it's confusing. There are some confusing things here, and there's some people online that present them really great. In fact, there's a good one I'm going to mention too while we're here, which is the crash course. So let's say action potential again. Now, I don't know if you know these crash course things. I recommend them because they're generally very accurate. So the information they give is good information. And so I recommend them for that reason. They are fast. So let's give you a taste of what this would be like.
What's it like to learn math on Brilliant.org? Brilliant gets you hands-on to help you learn by doing.
What if everything you did, and thought, and felt could be communicated by pushing a button? It'd be like using the world's simplest app, one that just sends out a little ping, always at the same volume and length, to communicate everything from "it sure is cold in here" to "I love churros" to "boy, I sure would like to breathe sometime soon." Well, that is actually exactly how your neurons send all the impulses responsible for every one of your actions, thoughts, and emotions. When a neuron is stimulated enough, it fires an electrical impulse that zips down its axon to its neighboring neurons. But they've only got one signal that they can send, and it only transmits at one uniform strength and speed. What they can vary is the frequency or number of pulses, like this is distinct from this. And your brain can translate these signals, reading them like binary code, organizing them by location, sensation, magnitude, and importance, so that you know the difference between "turn up the thermostat" and "oh my gosh, I'm on fire." That buzz, that nerve impulse, is called the action potential. It's one of the most fundamental aspects of anatomy and physiology and
Okay. You get the idea. I'm just going to flip back here. He's coming at you fast, right? Hitting you with all sorts of stuff, hitting you with animations and all this. I don't know if it's the best way to initially learn, but I'm a big fan of learn till you're confused. And then go looking for other things that can help you get beyond the confusion to a really much deeper level of learning. And I think that's what a lot of these things can do. So I really want to encourage you in this course and throughout to not just rely on what we're giving you, but to realize there's some really great teachers online, sometimes students who just went through this themselves, who present them well. Now, there's a danger that you're going to get false information. That's why you want to stick with more reputable kind of, like, even over here, look at who's giving you these things, and try to stick with more established, more respected kind of things. This one is fully respectable, I assure you, as is those those crash courses. As I say, they're quite accurate. They just come at you really fast. But it's fantastic for when you're studying too. You know, when you're getting ready for an exam, after you've studied a lot of this stuff, then you go to one of those crash courses, and it's really good for you to go, yep, okay, yeah, that makes sense. Yeah, that fits with what I know. What? Hang on. And so you can identify things where it's like, I missed that part, or etc. So that's my pitch. Self-directed learning. All right. So from there, then, I'm going to leave it here for now for this course. We're going to talk about more about how actual action potentials, not so much action potentials, but those neurotransmitters that are being released and how that affects everything. So I'm going to come back and talk to you about that next. But yeah, in the meantime, know that this is a challenging chapter. It's challenging in part because the terminology is hard. A lot of it is based on Latin words. It's biology, so it uses all this kind of fancy stuff. And a lot of the things it describes might be new to you. So, be very careful to monitor your understanding as you go. And if there's something you're just not getting, realize you have options. You have office hours if you want to ask me about it, but you also have the various online options to help you reach a deeper level. Okay, cool. Let's leave it there for now. I'll see you at the next video. Bye-bye.